Welcome back. Previously, we learned how to solve initial value problems, or IVPs, step by step. Today, we shift our focus to boundary value problems, or BVPs. Unlike IVPs, these can be trickier, especially with nonlinear equations. Let's simplify the complexity together. Each video in this series connects to the last, building your skills one step at a time. Be sure to follow along in order, and don't forget, practice makes perfect. Solving boundary value problems presents significant challenges. Many traditional methods generate solutions as discrete points, which may lack efficiency and precision. Furthermore, nonlinear BVPs are notoriously difficult due to their complex nature and sensitivity to initial guesses or boundary conditions. We're excited to introduce a novel approach developed by Hamid Semiyari. This method provides accurate approximations for boundary value problems with both linear and nonlinear equations. It improves computational efficiency and ensures precision through a simple yet robust algorithm, making it a powerful tool for solving complex BVPs. Join us as we delve into Semiyari's innovative method for solving boundary value problems. We'll explore its mathematical foundation and provide practical demonstrations to showcase its accuracy and efficiency. Let's embark on this journey into advanced problem solving. Now that we've set the stage, let's dive into the fascinating world of two-point boundary value problems. To fully understand and solve these problems, we need to consider the boundary conditions. These conditions specify the values of the solution at the endpoints of the interval. They're essential because they guarantee the uniqueness of the solution and ensure it aligns with the specific problem at hand. With these conditions in place, we can confidently proceed with solving BVPs and exploring their applications. Let's break down a two-point boundary value problem step by step. First, we have the differential equation, which is central to our BVP. This equation describes the relationship between the unknown function and its derivatives, and forms the core of our problem. Next, we turn our attention to the boundary conditions. These conditions specify the values of the solution at the endpoints of the interval, giving us the necessary constraints to solve the problem uniquely. Since our equation involves the second derivative of the unknown function, we classify this as a second-order differential equation. The second derivative represents the rate of change of the slope, which provides deeper insights into the behavior of the system we're modeling. The modified Picard's method is specifically designed to solve initial value problems, where all conditions are given at a single point. This method works effectively, provided that the function f satisfies the conditions outlined in Picard's theorem, ensuring that the solution exists and is unique. If, instead of the condition, we would be dealing with an initial value problem instead of a boundary value problem. In that case, our next step would be to convert this second-order differential equation into a system of first-order equations. We'll show you exactly how to do that in the next slide. By introducing an auxiliary variable, u, such that y prime equals u, we can convert the second-order differential equation into a system of first-order equations. This transformation simplifies the problem and sets the stage for more efficient solving methods, which we'll explore further in the next steps. Now, we've transformed our second-order initial value problem into a system of first-order ordinary differential equations. The key step was introducing the auxiliary variable, u, where y prime equals u. This conversion not only simplifies the problem but also allows us to adjust the initial conditions accordingly. Now, we can solve this system using methods designed for first-order ODEs. Since we have reformulated our second-order ODE into a system of first-order ODEs, we can now apply modified Picard's iterations to solve the system. This method allows us to iteratively approximate the solution, starting with an initial guess, and refining it with each step until we converge to the correct solution. One of the key challenges with boundary value problems is that, unlike initial value problems, we don't have an initial condition like. Instead, we're given a boundary condition at the other end of the interval, such as. This difference makes the solution process more complex, as we need to find a solution that satisfies both the differential equation and the boundary condition, which often requires more advanced methods. In boundary value problems, we often encounter situations where the value of the unknown function, or one of its derivatives, is missing at the initial point. This missing information complicates the process of finding a solution. A crucial question arises: how can we use the known boundary condition to estimate or obtain this missing value? Addressing this is key to solving BVPs effectively. Semiyari addressed the challenge of estimating the missing value in boundary value problems by reformulating the differential equation in its integral form. This approach allows the known boundary condition at one point to be used systematically to estimate the missing value, whether it is the function's value or its derivative, at the other boundary. By bridging this gap, the method provides a clear and practical way to proceed toward a solution. The details of this process will be explained step by step in the following slides. To advance the process, let us take another look at the integral form of the differential equation. First, we evaluate the integral at t equals b, the boundary point. Then, we substitute the boundary values directly into the integral expression. This substitution links the known boundary condition to the missing value, forming the basis for the estimation. In this step, we solve the integral equation for gamma, the missing value we aim to estimate. By isolating gamma within the equation, we establish a relationship between the known boundary values and the unknown parameter. This forms a crucial step in completing the solution process. A crucial step in solving boundary value problems is selecting an initial guess for gamma. A simple and effective approach is to use the slope of the straight line connecting the boundary condition points. This provides a reasonable starting point, ensuring the iterative process converges efficiently toward the solution. The innovative aspect of this method lies in incorporating the expression for gamma into the modified Picard iteration scheme. This allows for successive approximations of the unknown function and the missing value. With each iteration, we refine the solution for the function and the estimation of the missing value, leading to an increasingly accurate result. This algorithm iteratively refines estimates for both the unknown function and the missing value, gamma. By continuously improving these approximations, it provides an efficient method for solving boundary value problems and obtaining accurate solutions. We will now illustrate the method's efficiency with both linear and nonlinear examples, comparing the results to the known exact solutions. The computations were carried out using Maple, a powerful software tool for mathematical analysis, to demonstrate the accuracy and effectiveness of the approach. Numerical solutions for differential equations are carried out by implementing mathematical software tools. In these videos, I've used a symbolic programming tool called Maple. However, you can also use non-symbolic languages like MATLAB, Python, or even R to solve these problems numerically. These programming languages offer powerful capabilities for handling both linear and nonlinear differential equations. If you're enjoying this video so far, don't forget to like it, share it with others, and subscribe to the channel for more videos like this. If you have any questions or thoughts, drop them in the comments below. We'd love to hear from you. Now, let's apply Semiyari's method to an example of a linear boundary value problem. In this example, we will go through the steps of using Semiyari's method to solve the problem, illustrating how the approach can be effectively used to find accurate solutions for linear equations. Before applying the method, we need to provide initial guesses. These initial guesses serve as the starting point for the iterative process, enabling us to refine the solution step by step. Now, we set up the iterations for the method. In each iteration, we update our estimates for both the unknown function and the missing value. In this step, we plug in the known values into the equation. By substituting these values, we simplify the expression, which allows us to progress further in the iterative process. Now, we will compute the first approximation. Though it is feasible to perform this manually for the first iteration, it rapidly becomes unwieldy as the number of iterations grows. This is where mathematical software becomes vital. Tools such as Maple and MATLAB facilitate the smooth execution of the iterations, saving time and ensuring accuracy in numerically solving boundary value problems. Let's continue with the calculation for the first iteration. As we proceed with more iterations, the values will converge towards the exact solution. Mathematical software helps manage these iterative steps quickly and accurately, especially as the complexity of the problem increases. While the solution is accurate in its symbolic form, it may be easier to understand if we express it in decimal form. Converting the result into a numerical value helps provide a clearer and more intuitive understanding of the solution, especially for practical applications. We had the exact solution to the boundary value problem. In addition, we computed the first 5 iterations for the unknown function. The first 5 approximations of the missing value are also provided. As we expected, the value of the missing parameter is steadily approaching its exact value of 1, demonstrating the effectiveness of the method. In this slide, we compare the fifth iteration of our approximation with the Maclaurin series expansion of the exact solution. The maximum error in this fifth approximation is negligible, indicating a high degree of accuracy. We now present a graph showing the error in the fifth approximation. As we can see, the error is minimal, confirming that the fifth approximation is very close to the exact solution. The method we've discussed is surprisingly simple, and you'll be more agreeable when we show how it can be applied to solve nonlinear boundary value problems. As a result, the code we used is also straightforward and concise. In this slide, you'll see the Maple code we utilized to compute this example, demonstrating the efficiency and simplicity of the approach. Although the problem we've solved so far was linear, the method we use extends seamlessly to nonlinear problems. The primary difference is that the system of ODEs becomes slightly longer due to the introduction of auxiliary variables. However, the underlying difficulty of the algorithm remains unchanged, which is a significant advantage. Unlike current methods, where the algorithm becomes much more complex when solving nonlinear problems, our method maintains its simplicity and efficiency, making it an excellent choice for both linear and nonlinear boundary value problems. Now, let's introduce an example of a nonlinear boundary value problem. As you'll see, the system of ODEs is slightly longer compared to the linear case due to the inclusion of auxiliary variables. However, the underlying algorithm remains just as simple and effective. We will also provide the exact solution to this nonlinear problem for comparison, demonstrating how our method can handle both linear and nonlinear cases efficiently. In order to handle nonlinear boundary value problems, we introduce auxiliary variables. The goal is to express any non-polynomial function and its derivative in terms of a new variable. Once we define these auxiliary variables, we compute the derivatives and substitute the results into the system. This substitution ensures that the system of ODEs consists of differential equations whose right-hand sides are polynomials, which guarantees smooth and efficient computation. This step is crucial for simplifying the nonlinear problem and making the algorithm just as straightforward as in the linear case. Next, we compute the initial values for the auxiliary variables. These initial values are crucial because they serve as the starting point for the iterative process. By defining appropriate initial values for these auxiliary variables, we ensure that the system is set up correctly for solving the nonlinear boundary value problem. These values are typically based on known boundary conditions or approximations that guide the algorithm in the first iteration. Now, we need to find the initial guess for the missing value. As we've discussed previously, a reasonable approach is to use the slope of the line connecting the boundary condition points, which provides a simple and effective estimate. We employ an iterative method to approximate the solution. In this slide, we provide the initial guesses. These initial guesses are based on the boundary conditions and the method we discussed earlier, offering a reasonable starting point for the iterative process. By refining these estimates through each iteration, we move closer to the exact solution. After providing the initial guesses, the iterations are. We refine the estimates for the unknown function and the missing value in each iteration. Each iteration makes the approximations more accurate, bringing us closer to the exact solution. Here, we present the first 5 iterations for the missing value, including the initial guess. As you can see, with each iteration, the value approaches the exact solution, demonstrating the convergence of the method. Now, we present the first 5 approximations of the unknown function. Let's now compare the 5th approximation with the first 6 terms of the Maclaurin series. As we can see, the 5th approximation is very close to the exact value, demonstrating the accuracy of our iterative method. This comparison highlights how the approximation converges to the exact solution as the number of iterations increases. A plot illustrating the error in the 5th approximation, compared to the exact solution, is provided here. As the plot shows, the error is minimal, demonstrating the accuracy of our method. This visualization helps confirm that the method effectively approximates the solution with high precision after just a few iterations. In conclusion, our method provides a simple yet highly efficient approach to solving both linear and nonlinear boundary value problems. The iterative process ensures convergence to the exact solution, with minimal error, as demonstrated by the approximations and error plots. The ability to handle nonlinear problems without significantly increasing the complexity of the algorithm makes this method a powerful tool in computational mathematics. Overall, the method is both accurate and computationally efficient, offering a practical solution to challenging BVPs. At Mitra Institute of Education, we recognize that personalized learning is key to academic success. Whether you're just starting your educational journey, preparing for college, or working on your thesis, we're here to support you every step of the way. Our team comprises dedicated PhD educators with years of teaching experience, committed to helping you achieve your academic goals. Visit our website at mitrainstituteofeducation.org to learn more and get in touch with us today.